Hello, my name is Juan Scott. I'm the Executive Director of the 3MF Consortium, and today we have Kirill Volchek from Oqton, who's going to be presenting on Hybrid DfAM, using in part a carbon capture case study, and then deep diving into Oqton software. Okay, Kirill, take it away.
Good morning, good afternoon, good evening. Thank you for joining us today for this webinar. We are going to spend next half an hour talking about hybrid DfAM, and I would illustrate this novel approach to design on a couple of carbon capture case studies. My name is Kirill Volchek. I'm CTO at Oqton. I have about 30 years of background in the software development. Most of these I was designing, developing CAD/CAM systems. For about 20 years, I was chief software architect of Cimatron application. It's a CAD/CAM solution for tooling, molding, and die making. So that's about me. On our agenda today, a few words about Oqton, carbon emission, overview of hybrid tool set in 3D expert application. We'll go through carbon capture case studies, then conclusions and Q&A. Oqton was started about 5 years ago by Ben Schouwen, ex-Autodesker and professor of artificial intelligence, with a vision to revolutionize manufacturing with artificial intelligence and bring it to unmanned, almost autonomous level with a focus on additive, but not just, all different types of manufacturing, including. A few years ago, a company was acquired by 3D Systems to form independent software organization. Oqton is integrating all 3D System software assets today. Software portfolio covers various aspects of additive manufacturing, MES, starting from design to quality management. And one of the cornerstones of the portfolio is 3D Expert. And 3D Expert is in the focus of our webinar today. Carbon capture is a very important in current, we know everything that what happens with the climate. So we see rains, we see tornadoes, we see high temperatures, and industries are continuously growing. And even if we slow down our carbon emissions, they're still going to continue to rise on a planetary level. 10 years ago, we tried to limit global warming to 1 degree Celsius. Now we are talking about 2 degrees Celsius. But if you go to 3 degrees Celsius, it will cause a 2-meter sea level rise by the end of the century. And doing it in a green way is not enough. We need to remediate and pull emissions out of environment. If you want to stay below 2 degrees Celsius, emissions needs to become negative. And if you look into the map, we see everything which is like in the bluish color. That's something that potentially could be underwater by the end of the century. So what can we do? Carbon capturing can happen at the pollution sources from the ambient air. Capturing carbon at the source that is burning something. There is an ignition of fire where you burn hydrocarbon. In all those cases, carbon will be released into the atmosphere. Industrial process that make use of burners is a candidate for carbon capture. So we can redirect the exhaust fumes into the carbon capture system and get clean gas out of this. So what could be done? What we can do with carbon that is captured? So we can put it in the ground, or we can use it to create new products, plastic, glasses, cement. Many research organizations, startups have proven that it's cheaper to pull carbon out of the sky or from the exhaust chambers, then to mine it, which is huge advantage of carbon capture. So how process works? Pressurized air enters the system. A fan could be blasting air in, or a turbo pump could be injecting it into the system. Filters grab the carbon. Carbon is released from the filter in cycles, turn on filter. When it becomes full, turn it off, flush the carbon, repeat. There is a lot of downstream elements that needs to be dealt with, heat waste, phase transitions from gas to liquid, possibly the need to refine carbon. And all those stages, additive manufacturing could play a very important role, and as you can see, could solve complicated challenges and make process cheaper, easier. So if you look at traditionally manufactured parts, we can see this nice part, which is kind of traditional approach to manufacture lattices. It's labor intensive and has multiple stages of manufacturing, and additive could be really in place here. So turbo machinery, that's one example of what could be done with additive. Investment casting or direct metal printing provides faster time to market, cost reduction, reduction in waste, high efficiency. Heat exchangers, definitely something that we are talking a lot recent days. It could have things for additive, complicated structure, very efficient, complicated intensification structure. In this case, you can see that the implicit geometry. So also unifying complexity in one part provides longer lifetime and definitely more efficient components. This chiller, we are going to talk more today about it. So this is a very nice example of what can be achieved with additive, combining different types of geometries into one piece. Things for this design, it could provide just 4 seconds of stable chilling, up to stable chilling, microkelvins level of cooling gradients across XY plane. About 30 parts could be printed at once, so complexity is reduced. This quite miniature part could be put into the column, stacking it one by one. Another example of a device that we are talking today is a helical conductor. So thanks for this spiral design, it provides a vortex flow. So you can imagine the length of the path that we assembled into the spiral part to reduce the size. Still, the part of, is pretty large. About 500 components here, approximately combined into one single print. So yeah, on those two parts, we are going to talk more today. Before we are starting, a couple of words about 3D Expert. As I said, it's in a focus today. So 3D Expert is designed based on CAD/CAM platform. As I said, Cimatron about 7 years ago became kind of a ground platform to start designing and developing a 3D Expert solution. Inside this all-in-one solution today, we have all components that serves design for additive, lightweighting, topology optimization, starting from those elements through part preparation, creating supports, optimizing and looking into the printing process, or simulating a printing process mechanically or thermally, calculating scan pass. So all those aspects are covered with one solution. But today we are going to talk more about hybrid design for additive manufacturing part of it. Inside 3D Expert in seamless environment, we can design using different design paradigms. So everyone knows BREP. So this is pretty known way to design solids, surfaces also. So this is very nicely used and applicable in part design. So that's you can do in 3D Expert. Mesh for organic shapes, parametric beams for complex lattice structures, implicit for functionally generated shapes or complicated manipulations on shapes, and voxels we use for analysis and grid-based algorithms. It's important to mention that all those different types of geometries are created natively without reducing them to common denominator. So if BREP part or BREP element was created as a BREP, so you edit it as BREP, you slice it exactly like this. Same about meshes and beams and implicits and voxels. And very important to say that all those geometrical elements, all the geometry could be exchanged through a read-write with 3MF format, which we fully support, including most advanced extensions of the format. So today, there are discussions about volumetric extensions, and that would support also implicit formulations. So we would be happily joining this. So let's look a little bit more closer to this carbon capture condenser part. So it has a dual chilling circuit. Yeah, some process goes through those sinusoidal fins, and also cooling jackets that surround this part. Within those fins, we have a lattice structure for better thermal conductivity, but the precipitation happens with this semi-random, highly packed lattice, and this allows high efficiency of the process. So we have on one component also dual chilling and also capturing or carbon capturing process. And as we said already, this is, design allows us to stack it into the pipes. We perform CFD analysis of this design to ensure that we don't have a pressure drop and flow goes well through this dual cooling circuits. So let's have a look how this geometry works in 3D Expert. So we have this BREP external body, and using BREP functionality, we can change, modify, or create geometry. So in this specific case, we'll resize this hole for allowing for machining, post-machining. So making it's bigger. We can resize and change, let's say, rounds. So we are taking this round and modifying sizes of this round. Also, another round we are modifying. So those are BREP functionality in 3D Expert working directly on BREP bodies. And let's look at the lattice within the part. So this is stochastic or Voronoi, conformal Voronoi type of a distribution. It could be done purely based on the cell size, or it could be controlled by density. So let's say here we're starting this from this 4% of density going to 20% of density, and you see that change of the diameters of lattice allows us to really get this density automatically. So, or you can change cell size, and then you still keep the density percentage. About in this case, we keep the 30%. So this is about stochastic lattice creation, and let's have a look to this pseudo-random structure. So this looks pretty nice, interesting, and how it was done. So the source of this lattice is actually a simple diamond crystal, which was randomized with 0.3%. This coefficient, which could go from 0 to 1. So if you just remove randomization, we'll see very standard diamond crystal structure. So inside 3D Expert, you have the whole set of tools to create uniformal structures, conformal structures, as we have seen before, stochastic Voronoi type structure. Here we see, let's say, wirefell foam, a very nice, efficient structure for specific applications. You can design your own lattices. See, like we're just going through a couple of different types. So this is honeycomb structure. Those lattices in this specific case are beam based, and we can also change cross sections of beams. But let's go back to the original lattice structure, which is diamond crystal, and see what we can do for additionally with randomization. So randomization just takes each beam and breaks it to segments and randomizes slightly, but also we can randomize thicknesses. So now we can see that thicknesses are also randomized, varying it 3 times from lowest diameter to highest diameter. So could be very applicable to healthcare applications and for bone growth, but just as an example. Let's have a closer look as how this design works with dynamic sectioning. So actually outlets are located in the bottom. So we start from the outlet. So this outlet feeds those fins, and as we go up, we would see that those fins are start, and then we see like another circuit that actually feeds the cooling jacket around the part. Let's continue with dynamic section. We'll see another close-up to see beauty of this part. It's pretty complicated. And on top, let's continue a little bit more. And here we see already inlets. So one controls cooling jacket, and second goes into the fins. So this is what I wanted to show you in this case study. And let's go to the next case study. So this is a helical conductor. So part is large. It's a 1/2 meter by 1/2 meter by 1/2 meter part. As I said, many components were assembled into one. And this part has 3 functional elements of this. So first of all, it has gas conducting. Then it has a solvent shower head system within and cooling jacket around the part. So let's have a look how this part works. So again, we have BREP, and this BREP designed around the functional like inlets of a part of this. So here we have gas and coolant inlets. On top we have gas and coolant outlets. And if you look into the cooling jacket that spirally goes around the part, so those are cross sections of this cooling jacket. Solvent goes in, climbs up, and goes out through the set of shower heads, washing out the captured carbon. So so now we see this shower head design, which is done in the BREP. Like it's pretty complicated set of channels. Yeah, I can then close up. So through this holes, this shower head washes out, captured by the lattice carbon. So now let's look at the lattice. Lattice was designed in a conformal space, so it needs to follow this spiral internal path, internal channel. So, oops, sorry. Let me jump back briefly to this. Okay. So this internal channel was designed using 6 pairs. So it's topological cube. So we specify this six pairs of faces, and then system creates this conformal parametric volume that is used to populate it with a lattice. So this is a type of a cell we use for the lattice. So it's kind of 2x intersecting 2x pattern, and it should have a thickness of 1 millimeter in the cross section. But in order to solve a printability issue and to get low cost of a part, we had to really put all functionality of 3D Expert and also enjoy throughout a flow of the data representation within the system. So when we tried first to slice this part with this volumetric representation of the lattice, on a machine estimation was 3 weeks. So it's definitely cost a lot. So we had to reduce the slicing time, machine time to about 1 week, so 3 times. And in order to achieve it, we had to rethink the way how this lattice is actually sliced and produced, manufactured. So instead of really creating a volumetric representation of the element, we created zero thickness fins, and we put zero thickness fins into this conformal structure. So why zero thickness fins? I'll show you this on the later on the slicing, why it was very important for us. So here you can see that in the variable sizing of the cell, which is derived from the conformal structure of the spiral shape, we have those fins and those cells being smaller as you go closer to the center and larger that you go to peripheral part. Now you can see that like between tips of this lattice, we have pretty large distance, about 12 millimeters. So it's definitely not self-supportive, and we need to take care of supporting the roof of the channel. In order to do this, we integrated into this lattice additional cell, which is topologically fully connected with the previous lattice. But this top layer of lattice has special additional fins that serves as a supporting structures. So let's talk about slicing. The best and fastest way to slice and scan on a machine this geometry would be to just go in parallel passes. So that's fastest. We had to get 1 millimeter of a thickness, which we achieved by 3 hatches or 3 parallel lines located in distance of about 300 microns. So, and this allowed us to really reduce the printing time dramatically. So here I'd like just to stay for a second and just small feature of 3D Expert. As you can see from this join point, we have quite 5 fins that are going up from this point of a join. So if each fin creates 3 lines, you can think that just above this join point, in theory, without any special processing, we can get here large number of these parallel hatches located on almost same location on the part, and that would definitely cause overheat and overmelt and crash of a build. But in 3D Expert, we are capable to, because we understand what we are slicing, we are capable to reduce this problem, actually to eliminate this problem by removing unnecessary lines locally that derive from the structure of the lattice. So that's how this scan this lattice works, and that would allow us to really print this part in requested not 7 days but 8 days. So this wraps up also a second case study. As I have a conclusion slide here, we'd like to call it like not just hybrid DfAM, but we are really stressing that M letter. So we are bringing manufacturing into design for additive manufacturing. Thanks for 3DExpert hybrid DfAM capabilities that is capable to deal with highest complexities, finest details, and total manufacturability. So I would be happy to answer your questions, and thank you.
Thank you. I have a few quick questions. When we're looking at the hybrid DfAM, in this instance, we're talking about the hybrid modeling processes. So you have BREP, mesh, parametric beams, implicit, and voxels. Are they all running simultaneously within the same canvas, or do you need to switch across to different functions to achieve different parts of this modeling process?
They're running into single environment. So actually double clicking or modifying geometry or touching geometry, that is BREP, would give you BREP tools. When you do same for lattice, you'll get into the lattice modification or creation dialogues. So it's a part of portfolio simultaneously existing in the ribbons. So you have a ribbon for DfAM where all types of geometrical creations are in front of you.
So when it comes to exporting the hybrid geometry from these different processes for slicing, that's all taken care of, and you don't need to send out 5 different formats to the slicer. They're all going simultaneously from your system to the machine.
Yes, it goes simultaneously. It goes through different formats. So in some cases, you can use 3MF to export the geometry. And then again, you're doing like export of a part. So you don't have to export it 5 times.
Yeah.
You just export the whole, and you know how to convert, for sake of export, let's say, geometry into the format that is required. When we slice it and we process it through our slicer, so again, we know how to blend all those technologies together. In some cases, it's very interesting and not trivial process to blend different geometries and different technologies and different laser parameters and different scanning strategies into one single piece. But that's what 3DExpert is known for.
Yeah, and so when we think of hybrid modeling, we also think then of hybrid manufacturing. So how does the geometry or machine commands go across into other processes such as machining, milling, like surface finishing?
Okay, so in many cases, when you are working on a part, so you're preparing this part for manufacturing, first of all, you can load or you can express design intent through NGD, and then you can see what specific requirements for specific surface finishing you may have on a part. So then you can create machining offsets. You can close holes, then you drill afterwards. So all this exists in the environment of 3DExpert. All those manipulations that you're doing or geometrical mending that you're doing exist there. You can also counter warp your part actually to reflect and compensate manufacturing processes. Let's say additive manufacturing known to kind of a little bit change geometry of a part that you print. So you contour warp, and you can also compensate for this. But what's also important, the information that we created, let's say you close the hole or you edit manufacturing offset, machine offset to a part, it's export it to another. If you use different software that you plan your manufacturing, it could be exported together with also non-geometrical information. And then, there are different types of post-processing people are applying. It could be different polishing, surface finish operation. Many times in additive, you know that manual support removal is most popular way to deal with parts in metal.
Mhm.
But definitely machining also could be done, because again, we know geometry, we export geometry, we know where part is, and when we know where stock is, right? So that we can export both part and stock to software that actually performs machine operations.
Once you've made those modifications for the manufacturing process, how do you track and store that information in a PLM or MES system so that we can reference it in the future?
It's a very good question. When we are talking about this type of modern geometry, such as lattices or implicit geometries, I would say that some PLMs are more advanced and are already capable to to be able to import some geometries back from such systems such as 3D Expert.
Mm-hmm.
But in some cases, we can just save files within PLM. So some PLMs are capable just to save auxiliary files. So you can save 3D Expert file close to your original design. We also practice export of the bounding volume associated with density, center of mass, and moment of inertia attached to it. So in some cases, in the main design and assembly design, you don't really need exact high fidelity geometry, but you need like to get properties of this volume. So we also practice export of volumetric properties.
In one of the slides you showed CFD analysis driving the geometry. Was that internal simulation to Oqton, or was that external data coming in? And if it was external, how is it communicated into the software?
So in this specific case, we use external product. We have few, I would not disclose it, but we are working with and talking with leaders in simulation, CFD simulation, to integrate solvers into 3D Expert. Because actually the problematic is very clear. So those types of geometries, and when we are talking more about lattices or we are talking about implicits, they're not so CFD friendly types of geometries. So when we start exporting, and usually export could be done from meshes, so we are going to reach gigs of data that needs to be loaded. And yeah, it's not trivial for CFD also even to process meshes, because you need to have good boundary layers, and then it's not simple domain. We are working right now to have a solution built in into 3D Expert. It might take some time until we are ready for release. But just to say, like, we have within 3D Expert, we have static linear solvers fully integrated. So you can load your part with static linear loads, with vibration, and simulate it directly within 3D Expert. So we have FEA solvers working within a solution. CFD yet to come.
Okay. And then finally, on the slicing of the lattices, I understand how having the single toolpath is the most efficient way, or three toolpaths, depending on the thickness, is the most efficient way to communicate lattice. Like trying to hatch lattices without knowing the direction of the strut or the fin is not going to work. And to do that, you obviously have to have the ability to control the laser, which I understand is possible for 3D systems machines. How does that work with other systems?
I would say the different OEMs, they have different strategy how software could communicate with a machine. We are working with, I would say, probably 100% of metal OEMs, maybe 99.
That's a good
are
number. It's a good start.
with majority. Some of them, let's say, I would say for SLM, let's say for SLM solutions, we are controlling laser parameters. So we have with many OEMs, we are working in dual ways. So we can control directly from 3D expert slicer. We can control laser power and all scanning strategies, but we can also work through SDKs that OEMs are providing. So in some cases it's dual, so we can do both. In some cases we can do only SDK.
Okay.
So there is, I would say, half of vendors we are controlling laser motion. So and with half of vendors we are working directly through SDK. So
okay. What do you see the benefit of using 3MF as a data transfer between other design tools and manufacturing processes in Oqton?
So first of all, 3MF is the format where whatever geometry you have, so different type of representations, could be exported or imported at once. So you're not dealing with a set of files or a set of export import operations. So first of all, that simplifies the process. Secondly, expression level of 3MF. So you can not just export geometry, but you can start dealing with internal properties of the geometry. So colors, translucency. So properties, different types of properties could be also expressed through 3MF, which is absolutely advantage. Third, I would say is the file sizes. File size of 3MF known to be much smaller than, let's say, mesh SSTLs or mesh types based formats.
All right, thanks, Kirill. To learn more about Oqton software, visit Oqton at oqton.com. And to learn more about 3MF file format for additive manufacturing, visit 3mf.io. Thank you all for your time today.